Perfect. So our next speaker is Jaggi, who's leading the machine learning for optimization laboratory at EPFL. Take it away, Martin.
Okay, thanks a lot for the invitation and for organizing this nice workshop. This should be a good follow-up on the co-teaching we had before. So it's also about collaborative learning and teaching. I would keep it high level, but trying to give a few building blocks that we need for, or that we can use to have different agents learn together. And yes, so the very basic setting is coming from standard distributed learning when we have different users or agents which each have their own data set. But the goal here is to train a model which is good on the union of all agents, right? The union of the whole data set, which you see on the top right. But we want to keep the data on each client. So this is how you train large models on large data sets now in data centers, but our focus here is a bit different. We would rather think of this as maybe in the federated setting when we do this for a different reason, for the reason of privacy, that the data remains where it is. Of course, we use gradient-based methods for now, so we haven't gone yet much to distillation methods, which would be a bit more general, which would relate to the previous talk when we also ask about where the training signal comes from. But for us, it's simple gradients here. Yeah, federated learning I already mentioned, and the motivations are many of them. For example, you have different hospitals which are not legally allowed to send the data away, so they're kind of legally obliged to use a scheme like that. So you could then still enable them to train a joint model, or on devices, for example, the next word prediction when you write on your phone. So, but this is kind of only an intermediate step, which gives a bit better privacy. But what I'm kind of much more motivated for is to go one step further, which is to go to the real collaborative learning. And the difference on the right side, what we call decentralized, is that for one difference is that there's no server anymore, so that the clients kind of self-organize who they want to learn with, and when they want to do this, and how they select their collaborators, and most importantly also like what they want to learn. That's a major difference between federated learning, where the goal is the sum of each agent's tasks, to the decentralized setting on the right, where everyone can have a different task. So this is why I think it's a bit more pure, that yeah, maybe people have different goals, different tasks, but they still can ask, can I get help from other agents to learn my model to do better on my task. So this is a bit the setting where we want to go, but we always do the easier setting for federated as a first intermediate step. So, and maybe today I just want to briefly touch on two aspects, and one of them is when some of the agents are malicious. So they're giving us like bad gradients and so on. They're trying to break the system. So what can we do then? They're trying to poison the data. And then in a second part, I want to talk just briefly about the collaborative setting when everyone has a different task, what we can then still hope to achieve if you can, how much help can we get, and how do we benefit from the collaborators. So that's the plan for the next few minutes. So the setting with adversaries is quite simple. So as before, we have 5 workers, and some of them are the regular ones, the white, the yellow ones, and some of them are malicious, intentionally or not, right? They also just might be faulty. This is it's very related to fault tolerance as well. I mean, some might just fail, but some might fail for even a bit more malicious reason. They are actively trying to break the system, so they're going to send you gradients. They send gradients to the server, which are totally wrong. They can send arbitrary messages. So, for example, they can just send you the negative gradient of the true gradient they should normally send, and then hope that this is gonna derail the system. This is also related to data poisoning, but data poisoning is kind of a weaker notion, because there you would say, okay, I send you a gradient, but it's from a poison data example which I handcrafted. But here what you send can be anything. It doesn't need to be a gradient. So the malicious workers can send whatever message they want. And what we hope is that we could still train if the overall fraction of malicious workers is kind of manageable. Let's say half of them are malicious. Like usually this we cannot do, but maybe 20% are malicious, something like that. This is called a Byzantine robust training setting. And yeah, just to give you the basic solution approach, which is has been known for many years, not by us, but by many groups have worked on this. So traditionally, you just average all gradients, and now you need something else because obviously the average is not robust. So one bad entry can spoil the entire average completely. So what you do, well, you replace the average, the mean, you replace it by the median, for example. And we know median is a more robust quantity than the mean, but we have to be a bit precise. What do we mean by more robust? But let's think of one concrete example. Is, for example, let's just do the coordinate-wise median of these 5 entries that we get, right? So every gradient is a huge vector, and we do this entry-wise. We just use the median for every coordinate. But there are other methods too, and I will show you a simpler one later on. But this seems a reasonable algorithm. The question now is, could we analyze it? Could we still say that the new algorithm converges anyway with good workers, and then also does it converge when we have presence of bad workers? So there is one result which we were thinking about, which is asking that, like, if you just ask this question here in every time step separately, just like now today I will decide these are my good workers, and I will average with them. If you don't remember who sent you the bad vector, if you don't try to build knowledge and learn who are the good workers and the bad ones, then you cannot learn. And this is the result here, that if you don't remember who sent you what, if you just ask in one iteration, can I solve this problem, then the answer is no, because you can be fooled by people changing their position. You don't know who was sending the bad entry, so you need to kind of keep track and learn, because there's so much noise, right? Every gradient is already noisy, and then on top of that there is even more noise from being malicious. So these two things, you want to kind of try to keep it apart. How can you reduce the noise to see more signal on who is malicious and who is nice? So one super simple method would be to just use momentum on the past steps you have done, right? Momentum is very standard anyway in deep learning training, so let's just use it. And we use worker momentum, which means like locally on the client, we keep moving in the directions we used to. I mean, often people use this from an optimization point of view. They try to speed up training. That's not the purpose why we use it here. Here we use it for a different reason. We use it to have a more stable reference point on what is good and what is malicious, right? To have this reference point to then use this reference to aggregate the stuff around which we think are good gradients. So yeah, exponential moving average, very simple. It removes a lot of the noise, so then hopefully there will be more signal. And if we have that, then we can use the standard aggregation rules, which could be the mean or the median or whatever you want, but not on these noisy original gradients, but on the momentum stabilized ones. That's the algorithm. What aggregation rule? One that is simplest here is even simpler than the median thing I told you. The simplest one here, I think, is just to use clipping. So you look at the norm, you look at the Euclidean norm, how far away are you from the reference point? The reference point is MI, the momentum stabilized update that you as a worker were always doing, and you can always trust yourself. That's why the MI is something you trust. And these V's are the vectors you receive from the other workers. You don't trust them. So now the the question is, yeah, if you just clip them to the reference point, then you hopefully stabilize them around something that you trust as being good. And this works well. And another small remark I can make is that, I mean, clipping is not a bad idea anyway. So there's other reasons that people do clipping anyway in deep learning. Here we just say, let's also use clipping to achieve the Byzantine robustness. And then if we think about this, so then we can sometimes also analyze this. So there's some assumptions are here. So for example, this is only true if the data on each worker is still IRD. So this is a bit of limitation. But here what we analyze is if there's a fraction delta of potentially malicious workers, and the regular workers have a sigma amount of noise, then we get something which resembles the traditional SGD convergence rate, which is basically what we have here. If we forget about the delta, then you have what we all know. And the nice thing is you get the speed up with the number of collaborators you have. So if you have, there's n people present, there's n times as much gradients computed. So you hope this is good for something, right? You hope that these n additional GPUs you have, they also give you something good, that you should be n times as fast. So that's what we usually get. But can we also get this when we have malicious workers? The answer is it depends, right? If the delta is 0, then yes. But if the fraction of malicious workers gets larger, then you see that will be less speed up, right? Eventually, there will be no speed up for n in n anymore if the delta is significantly large. If the delta becomes as big as, I don't know, large, if it becomes a dominating part in the sum of these two terms, then you don't benefit from n anymore. Okay, so this is convergence, and it's only to a local stationary point. It's not a global convergence, of course, but at least it's applicable in non-convex if you have the standard settings. Yeah, that would be the first part. And in the next few minutes, or if there's no question, I would like to discuss a bit if we go to then heterogeneous data, and if we can also do a similar thing like that in the decentralized setting on a graph. So, was there any question at this point? Yeah.
I have a question. Some of the Byzantine militias, what kind of update they will do? You will simply arbitrarily change some inputs or some string, or maybe some grading ascent or inheritance or something.
Yeah, that's a nice question. Like, what are the bad things that these workers can do? And the nice property about this analysis is that there's anything is allowed. We have no assumption. That's why it's called a Byzantine setting, right? They're truly allowed to send any message. They're also kind of all knowing, right? The adversaries, they could collude between each other, but the only assumption here is that there's only, let's say, 20% of all the workers are malicious. Yeah. Then if you're a bad agent, what would you do? This is hard for me to answer, but well, standard attacks is like that you flip your label, which would then sometimes result in flipping the gradient. Yes, things like that. Yeah.
So in this result, the aggregator is fixed. Is that correct?
Yeah, you need an aggregator which has the nice property of robustness. The one I showed you on the previous slide does have this property. There might be other aggregators who also have this property.
You basically help yourself here is to make sure that the client has this momentum, which has this consistent effect that when the client is adversarial, somehow this kind of shows up with the signal of momentum. You could potentially also try to somehow randomize the aggregator as well, right? So if the nice clients don't care, they're not attacking the network, they should still do whatever they are doing in computing their Mary gradients. But if you just constantly changing the aggregator, maybe the adversary needs to somehow adapt, and you could also use that as a signal.
Yeah, that's right. That's cool. Yeah, if you could think of a scheme that you would kind of make the adversary weaker, that the adversary wouldn't know some secret randomness that is used in aggregation. Actually, this I think is related to some thing people do when you have heterogeneous data. Then there is this kind of bucketing techniques where you do this kind of randomization, which maybe relies on that you assume the adversary does not know the randomness, but in aggregation you could use it. But here the aggregator is fully deterministic. But yeah, it's a nice avenue. Yes.
Can I ask a question?
Please, sure.
In this kind of robustness analysis, I think statistical efficiency and robustness are always trade-off relations. So can you somehow observe that kind of trade-off in this bound or some other results?
The statistical robustness.
Like you
well,
said 20% of the clients are malicious, less than 20%. If the ratio is different.
Yeah, I mean, you're right. There is something hidden in the O constant, which would depend on what you say, the statistical robustness. That's basically this kind of C quantity we are hiding a bit here. That is true. Yes.
The solution can be extremely conservative in the worst case, because most of them are good guys, but the solution is really conservative. Try to ignore most of the clients.
That's right, but these constants do not depend on n. So and at least n the fraction of malicious one is explicit here. So, but yeah, you're right. The constants matter sometime. Yeah.
Or that doesn't change.
Yes. Thanks. Yes.
So I think you talked about the cooperation among the neural networks, and how about the computation among neural networks? So if you consider it's a global workspace, we have different neural networks enter this space, but usually there's a communication bottleneck. Not all of them will enter this space to share knowledge. And of course, if there's a malicious client, we need to find out this malicious client. But let's assume they are all benign clients at this point. And even if the distribution is ID, we still need to find a group of clients that their knowledge is reducible for the given new task. So can you elaborate on how can we select a group of clients which are useful for the current given new task?
Yeah, I will get to that. I think, yeah, the intuition you should have that this is handled by the clipping, right? If an agent is not clipped, then it means that you trust them, they're good, you have selected them. But I think this will be more clear in the following when we think from each agent's task. So who should you select to collaborate with? And you basically use clipping, and then I will get to this when we move here a bit, because here that's actually really the next step, because I want to now ask the same question. What if these users actually have different tasks they want to solve, right? Because before federated is a bit strange, right? Because we pretend that there is a global task which is the sum of everybody's tasks. So I don't like this assumption in federated. In the decentralized, this is nicer, right? You could say everyone has their own task, they select who they want to work with, and they try to solve the task. But now again, that's related to what you ask. Like, so now, yeah, how should one user, who should they trust? And I will get to this. Basically, the answer will be, yeah, you again use your local reference point and you clip what you receive. And yeah, the ones who are cut, these are the bad ones, and the other ones are the ones you should collaborate with. So that's the idea. And yeah.
For the non-clipping, if the data is heterogeneous, no ID. So for the different tasks, the norm of the model is pretty much different. Even they are both belong. So if we use non-clipping, we can have a high possibility.
Yeah, you're right. If the tasks are very different, this becomes difficult. So, but this is something that is also on this slide. I will get to this, and that is still a bit challenging. So because yeah, because it's actually kind of impossible to distinguish if someone you're trying to collaborate with has a different task, right? Or if they're actually malicious. That's impossible to say, right? Because if it's a malicious one, it could just be that they have a very, very strange task. But there's no way I can distinguish being malicious from having a very strange task. So when we talk about this here, then we will assume a kind of a task similarity, which So now if you want to look at the middle of the slide here, then we see we have a zeta here, and that is exactly this kind of quantity how the tasks are related. So we use a very simple gradient as variance between the clients, between the nodes, right? So your gradient in expectation is how far away from my gradient. So this pairwise variance is the zeta here, which then affects the rate. So this is a very useful quantity, and I'll also get back to this in the end when we talk about the speed up we could get, where we also need task similarity. What is nice here is that you can kind of choose, right? You can choose what's a similarity level for the people you want to collaborate with. So it's kind of up to you. It's just if you want people very similar to you, you will define this clipping radius like that. You will find people who are, I mean, if you're lucky, there's a lot of people in this radius, and you will get benefit from them. You get a speed up for how many collaborators you find. But if you're unlucky and you're asking for very similar people, then you might not find enough, right? Then you might not find enough collaborators. So that's a bit of trade-off, which I will come back at the end again briefly. But here there is actually a bit another thing I also wanted to mention, and that's the dependence on the topology and the graph topology, who talks to whom. And that's another kind of interesting aspect. It's also a bit non-trivial because the thing is that if everyone talks to everyone, that's like federated, then things are simple. But if you're on a graph, the problem is that you can quickly get isolated and you can get surrounded by bad guys. So that's kind of the problem that can happen. So you see, if the top worker here is malicious, it's not a big problem because everyone else can still exchange messages. But if the one in the middle, this one, is malicious, if we suddenly split the whole network into two, so then it becomes impossible for the green workers on the right and on the left to exchange and to learn together. So this is the question is like, how many bad workers are there in your neighborhood, and can they take the dominance of your neighborhood? And if that happens, it's a big problem, right? So that's why on the graph it's a bit different, but there is a way you can still get a result here, yeah. And the assumptions are that the graph of the good workers is connected and has a nice spectral gap, which means it mixes quickly. And the other assumption is what I said about the similarity, that zeta. So if the tasks are similar enough and the graph of the good workers is still connected, then you can still get results. But this relates to the question I think you had, when they're very dissimilar, you will not get to a perfect optimum. You will not perfectly learn your task anymore because the others are different, right? So then there will be a threshold or error level that you cannot get beyond, and that it will depend on the heterogeneity of the task, the zeta. Yeah, this is a bit a summary for the Byzantine. I'll go quickly over over this one. I mean, it's very related to what we discussed, right? It's just again basically asking the same question now. I mean, forget about Byzantine, but now let's just talk about the heterogeneity, that you are worker F0, you want to minimize F0. Can you get help from other workers 1 to n? What do you mean by help? I mean, they give you gradients. So are these gradients good for you? Are they going to speed up your learning? Of course, you could just train alone, right? Solve the purple problem on the left alone. But these helpers here, they're willing to help you for free. So you give them actually a model X. They give you a gradient back for free. They are very nice, right? It's just that they are a bit different, right? So the gradient they give you, even if they're very willing to help, it might be a bit too unrelated for you. So you need to decide which gradients are helpful for you or not. If everyone would be IID, then I get these n gradients from others, and hopefully I'll be n times as fast. But here the point is really to think about, if it's not IID, if everyone has a bit of different task. This is also very related to mean estimation, which is a special case of that. If you just ask, I have a small data set, I want to see my mean. Other people have another well, they can get samples from another distribution, just their distribution. So you also, if they give me these additional samples from a different distribution, does it make me faster to estimate my mean? That's another special case of this question. And again, you need to make some assumption that the true means are not too far away and so on. But if they are, then yes, you can accept the help, accept these 3 additional samples, and yeah, hope to be n times faster when you have n collaborators. So now we want to do optimization, we want to do learning, right? So of course, what the simplest thing I can do is the thing on top. So I just use in every round, I get my own gradient. I get these helper gradients. I mean, I will always give a big weight to my own gradient. I trust it, but it's expensive. So I want to use the helper gradients as well. And I give some weights to them and have to decide on good weights. This is a bit tricky, right? Because they are biased towards my task relative to my task. They're not unbiased estimators. A slight variant you can do is you can try to correct. So, they have a wrong expectation, but maybe you can learn a shift. This is also related to like a drift reduction in federated learning when everyone drifts too much on their own task. Or maybe there's a way to correct it, to subtract something such that it becomes a better estimator for the gradient you want, right? And you want a gradient for F0. So can you correct for it, or could you you could also learn a more complex function which takes these helper gradients and hopefully maps them to something which is more useful for you as a agent F0 to make progress on F0. That's the idea. We only have some very preliminary result on the very strong assumptions. So here we need the task to have Hessian similarity. So basically the landscapes of each agent must be very similar to each other. If they are, then the gradients help to some degree. And one downside is also we need the similarity to become very, very high when the number of steps grows at the moment. But this is, I guess, a nice research topic. And I guess that's it. I have a advertising slide on software. We're actually trying to make a JavaScript software, which is a bit strange in machine learning, but it's nice because it runs in browser and so on, and you can play with it, and hopefully people can bring their new ML models, run it on the phone or whatever on the browser. And we try to have some of the schemes here, like federated, decentralized, and also you can have this robustness that I mentioned. So we have clipping supported, so you can have a bit of Byzantine robustness. You could also have secure aggregation if to slightly, give a bit more privacy to the gradients. So if anyone has expertise here, we would really like to get your help, and this is open source. Anyone's welcome. Yes, that's it. I don't want to take too much from your lunch, yeah? So, okay.
Thank you very much. So in the first part, so you use the momentum to robustify the solution rather than to accelerate the solution. So it is like a moving average, taking a moving average, like an exponential decay. So is there any possibility to consider other weighted average, like just taking the average of the history? So does it work? So
you mean history of your own agent or of the other agents? So
also in each age, so you can take the average of the histories and then we can aggregate that. So instead of just taking the exponential weighted average, so you can take the average, just a uniform average over the history. So yeah, my question is is there any other options to obtain the same convergence?
So, I think so, yes. We just took momentum because it was the simplest one, and we based the analysis then on this Kwiatkowski and Orabona paper, which is called Storm, which is analyzing SGD with momentum and using a similar analysis. The goal here is, it's not to accelerate, just to stabilize, as you said. So to remove the noise, yeah, and yeah, there might be other methods, maybe some variance reduction techniques. I don't know. It's a good question. Thanks.
Okay, thank you very much.
Can I ask a question? So this is not really directly related to your talk, but in this kind of distributed scenario, so are there any works that considers kind of distribution shift in clients? Some clients may have different, slightly different distribution, but still we want to utilize their opinion.
Yeah, I like this question because it's related. It's more about the sequential learning aspect. So I mean, because here everything we have, it's synchronized. Everyone is working at the same time, which is not realistic. But you're right. Like if a worker would, like just one of them works first, and then another worker takes their model and keeps working on a different task, then you're exactly in this setting of transfer learning, or also it's related. Yeah, this may be continual learning or so, or curriculum learning. That, yeah, what happens if you first learn task one and then you transfer and learn task two? Do you forget task one before? So we're also very interested in this. Maybe it's also, what if you run SGD, but with a strange order of data? So that's, I think, quite nice.
Thanks a lot. One question.
Okay, so let's thank Martin again.
Thanks for the question.